This is lecture number 10, chapter 6. So what we're studying actually is a cavity, or you can say a resonator. It's a concept of feedback that photons are moving to and fro, passing through the lasing medium number of times. Okay. Here, a resonator as an interferometer. What is interferometer? You have seen, or maybe you have studied somewhere, the Michelson's interferometer. Okay, so Michelson, this is I mean, like if there are two mirrors there and the light is like moving to and fro, to and fro, to and fro, to and fro, and then pass through one. So this is simply we call it interferometer. Okay, so what things are explained here, there are some terms are used like FSR. FSR means that free spectral range. From one pulse to another pulse, the range is called free spectral range. Okay. So FSR, free spectral range of the interferometer. Now, if you look at it, what thing is mentioned, as I explained earlier, that a laser cavity acts as a interferometer. Okay, which an integral number of waves must fit. Integral number of waves must fit. Okay, it depends on the length, and there are certain formula which we study in the next slide. Okay, so in other terms you can say it's a longitudinal modes concept. Second point, the cavity is resonant at wavelengths such that the number of waves inside the cavity is an integer. Okay, the cavity is resonant at wavelengths such that the number of waves inside the cavity is an integer multiple of something. So these standing waves, so what kind of waves are generated here is standing waves. Okay, standing waves are generated in the or inside the cavity, and the length of the cavity, it will decide the wavelength as well. We see in the next slide. So at all other wavelengths, what wavelength we choose according to the integer multiple of something. So all the other wavelength, they interfere destructively. Okay, and that extinguished, it vanished somewhere inside the cavity. Okay, so these resonant wavelengths are called the longitudinal modes. The resonant wavelength, okay, decided by the length of the cavity and are spaced apart at a regular interval of frequency. So the resonant wavelength are called the longitudinal modes, okay, and are spaced apart at regular interval of frequency, like here, 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 and the spacing between these two intervals is called FSR. So this spacing is called FSR, free spectral range. Okay, and this FSR, it depends on the wavelength, okay, intervals and this kind of things. Now, very important slide. So the distance between the cavity mirrors is L. These are cavity mirrors and the distance between them is L. Okay. The condition for the standing waves in the cavity, as we know that inside the cavity the standing waves are generated. Okay. So if this is the length of the cavity, how we can find out the wavelength with this formula? Okay. So if we know the length, we have to decide the length, or if we know the wavelength, we can find out the wavelength, or if we know the length, we can find wavelength, and if we know the wavelength, we can find out length. Okay. So basically, if we want to find out the lambda, then 2L over M. Okay, M is integer. Okay, for the constructive interference. So integer, and so the spacing FSR of the resonant mode in the cavity, FSR, free spectral region or range, is given by, so delta nu is equal to M C over 2L. Okay, it's a frequency. Now this is the frequency, here was a wavelength. Okay, so just a rearrangement of this equation. So like lambda is equal to C nu. Okay, so this is what it's mentioned here. I mean, just interchanging the concepts. So basically FSR we can find out with by using this formula. It will give the wavelength, this one will give the frequency, and this delta nu actually it's a spacing. Okay, it's a spacing like, and it will be in hertz. Okay, unit will be hertz. So for any interferometer, the sharpness of the resonant peaks, these peaks, for an interferometer we can find by using this one. So delta is equal to nu f over f. What is delta? That is full width half maximum in hertz. Okay, full width half maximum in hertz, and nu f is the frequency of the first mode when m is equal to 1, and f is the fineness of the interferometer ratio of the mode separation FSR to the spectral width. Okay, so this one f is fineness, and fineness is the ratio of mode separation FSR. These are frequency modes FSR to the spectral width. Okay, so this is fineness. Okay, so and here another formula which is where R is the total reflectivity of both the mirrors. Okay, here as the reflectivity of cavity mirrors increases, the spectral width of the peak become very narrow. Okay, and in most laser the reflectivity of the cavity mirrors is very large. So reflectivity increase and the spectral width become very narrow. Okay, and in most of the laser, what he says, the reflectivity of the cavity mirrors is very large. Okay, so fineness, this f we can also find out in the way pi r is reflectivity minus r. So हमने इस इक्वेशन इस सॉरी स्लाइड में क्या स्टडी किया है कि व्हेन यू वांट टू, इफ यू, अगर आपने कैविटी की लेंथ को डिसाइड करना है तो आप ये फार्मूला यूज़ करेंगे, वेवलेंथ जिस स्पेसिफिक वेवलेंथ के लिए आप चाहती हैं डिज़ाइन करना, एम इज़ इंटीजर फॉर द कंस्ट्रक्टिव इंटरफेरेंस. ओके, और जो कैविटी के अंदर जो है वो आपकी स्टैंडिंग वेव जनरेट होती हैं. एफएसआर जो आपका रेजोनेंट मोड्स हैं उसके लिए जो फार्मूला यूज़ किया जाता है उसकी लैम्डा की जगह पे आप यहाँ फ्रीक्वेंसी रखें और सी स्पीड ऑफ लाइट, और ये जो आपका फार्मूला बनता है. उसके अलावा You delta nu actually it shows the spacing in hertz of the modes, spacing of the modes here, here. Or for any interferometer, the sharpness of the resonant peaks for an interferometer. The sharpness of the resonant peak for an interferometer we can find out like this. Okay, the sharpness of the resonant peaks with this formula where F is a fineness. Fineness is the ratio of the mode separation. Okay, FSR to the spectral width, and this new F क्या शो कर रहा है, न्यू एफ जो है वो आपकी फ्रीक्वेंसी शो कर रहा है पहले मोड के लिए. ओके, उसके अलावा फाइनस यू कैन आल्सो फाइंड आउट बाय लाइक दिस रिफ्लेक्टिविटी, रिफ्लेक्टिविटी और 1/r. सो रिफ्लेक्टिविटी इंक्रीज करेगी तो आपकी जो पी बिकम वेरी नैरो ऑफ द लेजर. ये एग्जांपल है आपके बुक में. सो द थिंग इज दैट व्हाट इज इन दिस एग्जांपल इज an argon laser, 1 meter cavity spacing, has HR, reflectivity is 99.99%, and OC optical coupler with the reflectivity of 98.0%. So compute the expected spectral width of a single mode of the cavity. Compute the expected spectral width of a single mode of cavity. So expected spectral width, okay, of a single mode of the cavity. So single mode here, here, okay, so it's the FSR. So this new FSR MC over lambda, okay, which we have sorry in the last slide, and then substitute the values. L is 1 meter, okay, so 150 megahertz, okay, expected spectral width of a single mode of a cavity. So this spacing between the resonant peaks of the interferometer. Okay, now the fineness of the cavity may be computed first by calculating total reflectivity of the cavity. This pi r over 1 minus r. This is fineness. Okay, and total reflection here. So RHR, ROC. So 0.9799 is the answer. 0.99 is HR, and optical coupler is 0.98. So this is how you can solve this example. Try by yourself. Longitudinal modes. So longitudinal modes we already discussed a bit the previous slides. What do you see here? This is spectrum. Gain, wavelength. Okay, so this is a peak here. This is a gain curve for a practical laser. Okay, so the thing is that what is mentioned here is few of the points that real laser gain media do not have a sharp defined wavelength. In reality, the gain medium do not have a sharp defined wavelength. Okay, amplifier over a relatively wide range. Okay, amplify over relatively wide range, maybe spectrum is like this or something like this. In a gas laser, Doppler broadening we have already studied lead to the existence of a gain curve in which the gain of the laser peak at a center wavelength feet above. Like this it has to be, but like this it's because of the Doppler broadening what we have studied already. Okay, so at all points on the gain curve, where the gain is sufficient to overcome losses in the laser, at all points on the gain curve where the gain is sufficient to overcome losses in the laser. Okay, at all points on the gain curve where the gain is sufficient to overcome loss in the laser may oscillate and have output. So we already know at all points on the gain curve here where the gain is sufficient to overcome losses, here in the laser may oscillate, have output. Cavity itself is an interferometer. We already seen this thing, and is resonant only at a wavelength spaced apart by FSR. Okay, this is FSR. So N here is the refractive index, L is the spacing of the cavity mirrors, FSR in terms of frequency we usually calculated. Okay, so the number of modes that will oscillate simultaneously may be determined by dividing the spectral width of laser by FSR. Okay, so number of modes that will oscillate simultaneously, number of modes okay, so C, so N is the refractive index of the medium, L is the length of the cavity, and 2 definitely is any integer. Okay, so and FSR we can find out if we know all these values. So this is basically this concept is used for the longitudinal modes. What do you see on this slide? That is origin of longitudinal modes. Origin of the longitudinal mode. This is a gain curve. Okay, this is a cavity resonance inside the cavity. What is happening? And this is output of the laser. Okay, so what is happening here? That this is a gain curve. Here we see more efficient, okay, threshold values, and we see what is inside the cavity here. So this portion is inside this portion, and this portion is inside the cavity. Okay, so what we see at the output, we see this thing. Like this, what is coming here in between this region. So now what exactly explain here? The gain curve of the laser medium along with the lasing threshold, the point at which the gain equal losses. The point at which the gain equal losses in a simple model and output spectra resemble the shaded area on the top. This is here, this portion. So what is happening here? The losses is overcome by the gain. Okay, so gain curve of the along with the lasing threshold, the point at which the gain equal the losses. The point at which gain equal the losses. और इसके बाद in a simple model the output spectra saying resembling the shaded area. So यहाँ पे इस region में आपके ये जो gain है वो losses के equal हो गई, ठीक है. इस threshold value. Now दूसरी picture में क्या है, दूसरी figure में क्या है? The resonance of the cavity at frequency spaced by FSR with the FSR formula. This is the spacing. Okay, FSR. This is FSR, this is FSR, this is FSR. Okay, so this is happening inside the cavity. Now the output is seen to be several modes. What fit here? That is 11, with the strongest at the center of the curve here, where the gain is highest, and the weakest near the edges. This is the weakness, this is strongest, where the gain just slightly exceed the losses. So the laser cavity is an interferometer that a resonant mode of the cavity are spaced apart by the free spectral range. So this is a formula. So laser cavity is like an interferometer. Okay, and the modes of the cavity are spaced apart. We can find out with the FSR. C is equal C over 2 and L. So this is how the things are working. I mean, what are the modes, what are the longitudinal modes, and etc. This kind of things, and how you get the output. This the cavity, and this is the gain become equal to losses. So best fit here, this one, and then we get this is the maximum, this is a minimum here. So this is how the things are working inside the cavity actually.